Hello, thank you first for the invitation from the organisers. When I got the invitation, I was very excited, and then I thought, oh, Ben's an organiser, and maybe he wants me to promote his work, but then I've seen how many times his name has come up in almost every other talk, all in different areas, so I feel like maybe it's slightly less biased. However, my talk could easily be changed to the Ben van der trilogy today, because I'm going to talk about my own work on statistical inference using machine learning. But also I'm going to take the place of Justin Alsing for 2/3 of my talk, so just put his hat on my head for those parts. So a lot of this, of what I've said, on what I'm going to say has already been said in several other talks, which makes my job slightly easier, but means that you might fall asleep at times. But let's start with the very basics. So ideally, we want to do some statistical inference if we want to know something about parameters of some model. And in particular, for those Bayesians in the room, we can use Bayes' theorem, which relates likelihood to some posterior distribution. So the likelihood is the description of some data given a model and some parameters. This is great. If we know the likelihood and we can draw for some prior and we can just find out our posterior distribution. We can find out we can infer parameters of a given model using that. But it's becoming increasingly more difficult to write down a likelihood. Because we're going to regions which are non-Gaussian, our data might be very non-Gaussian, and it's becoming more difficult. So, what can we do when we're not able to compute the likelihood? Well, I've written it on the top of this slide, so you might be able to guess. So we can do one of our options. Well, there's many options. So, for example, we had the talk from Jens earlier today using Borg, where we can move our unknown. What we would like to know would be the non-linear posterior, but we can shift that back to the linear stuff, which we can understand, and then forward model and do things one way. This is semi-equivalent. It's approximate Bayesian computation. So what we do is we can simulate. We have good physical models. We can use those models to simulate our data from at a particular parameter value, and then draw from our prior. And then we can accept or reject a particular model parameter given, depending on how similar the data is to the simulation, so how similar the simulations are to the real data. And as Florent pointed out the other day, this should really be called likelihood-free rejection sampling and not just approximate Bayesian computation. So, if we try and do this naively, and we just take some data and we simulate it, and we try and compare our simulation to the real data, in principle, this happens in really high dimensions in the parameters, the dimensionality of the data. So we need some way of reducing that dimensionality to have any chance of getting close so that we can accept or reject. We're always going to be very distant from the real data in our simulations if we're in very high dimensions. So the first thing that you can think about doing is to use some summary statistics. So you go from your data, pixels or whatever, and summarize those using things like the power spectrum or higher order statistics. You can use things like PCA. There's many things that you can think of using. So let me just mention about what summary statistics will be available from upcoming surveys. If we try and take the power spectrum and other similar statistics from something like LSST or Euclid, we're still looking at of order 10 to the 4 summary statistics at least. So this is still not really a small parameter space. This is not a small dimension. It's still extremely difficult to hit these targets by simulating and accepting or rejecting. So, and each time you do this forward simulation, because you're in high dimensions, you need to do huge numbers of simulations if you're doing likelihood-free inference, and that's a problem. It means we need to use huge amounts of computing power. So what we would really like to do is, can we compress this down to a really small number, ideally, of parameters? Can we reduce the dimensionality of our problem down to the number of parameters that we have? So this is where I'm just in hat on for the first time. I'm going to talk about compression for general likelihoods. Now I'm going to talk about some statistics, which is very good in an inference conference. And I'm really going to go back to basics. So first of all, we have the Fisher information. This is just the amount of information that some data contains about some parameters in a model. And it can be thought about in two ways. The first one that's at the top here is that it's really the curvature of the log likelihood about some fiducial parameter value. So if you look at how peaked, if your likelihood is extremely peaked around your fiducial parameter value, then it's extremely informative. And likewise, if your log likelihood is very broad at the fiducial parameter, then the data is not very informative about your model parameters. And the other way to think about it is that the Fisher information is the variance of the score. So this here is called a score. It will come in useful quite a lot later. So, and it's a great statistic that we're able to use. We can, in particular, it features heavily in the information inequality. So this states that the variance of some unbiased estimators their variance cannot be smaller than the inverse Fisher information. So unbiased estimators are just where the summary statistic, this funny shaped T, gives you the expectation of that value is equivalent to the parameter itself. So obviously, we don't actually have to consider unbiased estimators. We can have a look at what the low bound on variances of any sufficient statistic could be. So in a sufficient, I say sufficient statistic here, it wouldn't necessarily have to be, but it's just some statistic which still has to follow this inequality, so that the expectation value of the derivative of the statistic, this quantity here, still has to be greater than the variance of the statistic itself. So let's have a look at if we can make an informed choice of what our sufficient statistics should be. And because I'm talking about it, it's clear that we can. So the first thing to do is if we can expand the log likelihood just about some fiducial parameter values. And this can be for any likelihood. We don't have to worry about it being Gaussian at this stage. So we just expand it, and we notice that to linear order, so only linear order, then the data is coupled only to the score. So it's this term here, the data is here. So it's this score function here. So one useful thing to notice is that this score, this here, is actually lives in the dimensional space of parameters and not data. So it might be a good idea to think that we should use this, and it goes that this is true. We should use this score as our set of sufficient statistics. So if we now plug in this score here into our variance, we calculate the variance of that score, then we notice that that is exactly the equation that I showed in the first slide, which is equal to the Fisher information. So that's one interesting thing. And the next point is that the derivative the sufficient statistic, the expectation value of that, is actually equal to the other term that the Fisher information can be written down as. So, given that these are both equal, we can now just have a look at the information inequality, and we can plug in this term on this side, and we can plug in this term here and this term here, and look at what this is, and we see that the left and the right side, left side and the right side are equal, which is fantastic because that means that this statistic saturates the information available. So, in other words, this statistic is a minimum variance estimator of the parameters. Right. So, let's now go back 18 years. To Alan Heaven's paper on massively optimized parameter estimation and data compression. And so we can consider everything which I've just told you and now assume that your likelihood is Gaussian. And by this I mean that all of the parameter dependence is in the means and not in the covariance. So here's our likelihood. Let us calculate the compression function. So this, again, will be very useful, so remember it. So our sufficient statistics are just given by the derivative of the log likelihood at some fiducial parameter value, and it's written here. So it's the derivative of the mean with respect to the parameters, and the inverse covariance, which acts on the data and gives us our compressed data vector, which is, as we can see here, can be written, so we can now just use this to get the log likelihood and put this into the Fisher information, and we can calculate this statistic. So, if we assume that our likelihood is Gaussian, and it actually is Gaussian, then this function here allows us to compress our data down to the number of parameters in the model without losing any information, because it saturates the Fisher information. So, how can we use this? This is excellent. We've just gone from data space down to parameter space in dimensions by a very, very simple calculation here. So what can we do? Well, the first thing is we can just take our data and we can calculate some statistics, some summary statistics, and just assume that you know that the likelihood is Gaussian. Because, as I've said here, this is only lossless compression when the likelihood is Gaussian. So if we find the power spectrum of some data, then we can assume that it's Gaussian and compress it using Moped. And excellent, this is one way forward. If we're in the case where we don't know what our likelihood is, or we don't want to, if we can't even calculate the power spectrum easily, then we can forward simulate to get realizations of something like the power spectrum, and then compress that and do ABC in that parameter space, in that dimension, which is great. But what I'm going to talk to you about, I'm going to take off Justin's hat and put my hat on, is that maybe you don't have to approximate your likelihood. So this is where we go one step forward. We've just looked at our linear likelihood-free compression or linear compression, and now I want to go nonlinear. So have a sip of water. Let's assume we start with some unknown likelihood. We don't know what it is at all. It's just some model which can generate some data with some parameters. And we don't know the shape of this likelihood, and frankly, we don't really care what it is. Our data has some likelihood. So what we'd really like to do is to see if there's any way that we can push our data to give us some summaries, where those summaries are Gaussian, and in the dimension of the number of parameters. So essentially, we're going from our unknown likelihood to this here, which looks very Gaussian, which is nice. And so here we've got this μf, which is the mean with respect, the mean of the summaries, rather than the mean of your data now, and this covariance is the mean of your, is the covariance of your summaries. And so we're just trying to Gaussianize this thing. But obviously, F sounds quite non-trivial. I mean, you could go ahead and try and guess a million different nonlinear functions to see which works the best, or you know, it's very non-trivial. But I mean, I wrote machine learning on my title slide because we're going to use a neural network. This is some way, a neural network is just a nonlinear function. And the best part about it is we don't actually care what the form of that is. This goes back to a point that Boris made the other day. On his 3 good uses of machine learning is point number 3 was just put all the stuff that you don't care about into the machine learning. And that's what I'm going to do. I'm just going to use the neural network, which is some generic nonlinear function, and use that to try and get these summary statistics. So here we go. We have a compression network. The compression network is, I mean, it doesn't have to be fully connected like this. It's just something which takes in some data, goes through some nonlinear transformation, and gives me out some compressed summaries from here, from 4 to 1. So what is a compression network? I mean, it's kind of in the name. So first of all, it has fewer outputs than the number of inputs. And in this case, we're going to particularly focus on the case where the number of outputs is in the same dimensionality as the number of parameters in the model. I'm just going to make a point about what your neural network should be like. And your neural network should be built for your purpose. One of the things which Shirley was saying was talking about how you can infer physical things from your neural network by putting data through your neural network and looking at how things change. And so can you learn from the neural network? But in the way that I think, then you should always design your network with your physical parameters in mind. So if you've got some data which is translationally invariant, then you should be using convolutions. And if you've got something which is rotationally invariant, then you should have some form of kernel which is rotationally invariant. And this is an excellent way to be able to safely compress your data quickly and efficiently. That was just a side note. So what we're going to do? Well, need some function that we want to minimize, and in our case, we actually want to maximize something, and that thing we want to maximize is the Fisher information. So, and because most people think of minimizing when it comes to neural networks, then we're actually going to just take the negative form of this. So let's see what these bits are. So here, this is just the form of the Gaussian Fisher information, the Fisher information for a Gaussian. And we have the mean of it's the derivative of the mean with respect to the parameters, and this is the mean of the summary statistics. So you put some simulations through your network, lots of them, and you calculate the mean of those. I'm going to show you in a second that it's quite easy to do the derivatives as well. You can do it numerically, but you can also do this non-numerically if you've got that available. And the covariance is the same. You just calculate the covariance of the summary statistics once you've put some simulations through your network. So what do your simulations need to be like? So first of all, you want your simulations to match your real data as well as possible. If they don't, then you're probably going to get some kind of bias during your compression. It's not necessarily true that you will, but the better you can make your simulations, the better. So Now, I've said that you need lots of simulations, but this is a very, very efficient network. It works on extremely few simulations compared to what most regression type networks do. And the reason is that we're going to train this network statistically. So we need simulations at a fiducial parameter because we're going to calculate the Fisher information, which depends on only the parameters at a fiducial parameter value. So this means that the only simulations that you need to be able to maximize this function is the number of simulations you would need to approximate your covariance. And this is the covariance of your summaries, not your covariance in your high-dimensional data space. So this can be relatively small compared to spanning all of your parameter space to make sure you can do your regression. But we do need some information about what's happening in the rest of away from the fiducial parameter value, and we can do that using derivatives, which we're going to use here in the mean. And we can do this in a couple of ways. We can either, some people are lucky enough to be able to get an analytic simulation, calculation of their simulation when they do a forward pass. So I know Borg is one of these. There's many others. And in that case, you can, I'm going to go forwards a slide. You can just use the chain rule and differentiate your network with respect to the data which you input. So this is, say we put some data D1 through your network and we calculate some summaries. Then you can also, more or less for free, calculate the derivative of these summaries with respect to your input data. And that's great. And then you just use the chain rule and multiply it with the derivative of your simulation to start with, and it's very cheap. And otherwise, you need to go to numerical methods, and going to numerical methods means you have to up the number of simulations you have to do, but still, actually, relatively, it's very cheap, given that if you suppress sample variance, then you can calculate the mean quite cheaply. You don't need many simulations to calculate the mean if you suppress sample variance, and this is great. It means that if your number of dimensions of your parameter space go up, then the number of simulations doesn't go up by the nth power of that dimension. It just goes up by some small factor which you need to do one extra set of derivatives. So it's really, really cheap. This is one thing I want to focus on. The number of simulations you need to do this is very small compared to almost any other machine learning method. So this is why you should really think about using it. So, like I was saying, you make many simulations, but not that many, and calculate their derivative or calculate some numerical derivative of your data. You pass those through your network. So this is only one network. I've put 3 here just so that it makes the slide look nicer. But there's just one network, and you put all of the simulations through at once. And you calculate the covariance, or the inverse covariance, and the derivative of the means with respect to the parameters, from which you can calculate the Fisher information. You take the determinant of that, square it, and then maximize that. So this leads to the next thing we can do. We've now got a network which can make summary statistics, which is sufficient if we can train it properly. So now what can we do once we've got those? So there's one thing. There's one thing which I haven't written on my slides. I realized I'm going to mention it now. Is that, as I mentioned several slides before, when I was pointing out how important something was, is that the sufficient statistics for general likelihoods are linearly related to unbiased estimators or maximum likelihood estimators. So the first thing we can do is we can just, I'm going to flick back, which is not what I wanted to do, but I'm going to do it anyway. So here, we've now calculated the derivative of the mean with respect to the parameters, and we've also calculated the inverse covariance using the neural network We can therefore just apply this to the data, and in this case, this would be our summary statistic, and we get a maximum likelihood estimator. So this is really cool. We've now got, not only do we have just some summary statistics, they're linearly related to maximum likelihood estimators. But I'm going to talk about ABC and likelihood-free rejection. So the first thing we do is we make the simulations at some fiducial parameter value, and we calculate the derivatives either numerically or analytically. And we train the Fisher information. That's nice to say, but you just have to keep putting your simulations through and keep updating the weights in the network until you have saturated how much information your network is able to pull out in your number of summaries. And then, you've got your trained network. You've got some real data, and you put that real data through your network, and now you've got compressed real data, and it's summarized by just the number of parameters in the model. Here we go, this is an example. You just put your data in, you get your summary out. So then you draw from your prior and draw some parameters, and you compress, and make some simulations at those values, and you compress those simulations. So here's another plot. So now you get some parameter-dependent compressed simulations. And then you just accept or reject the proposed samples to build a posterior distribution. And this is ABC. We can now calculate our approximate posterior distribution very, very easily. Not very cheaply, but very easily. So I'm going to go to example time, and this is very exciting. It's my favorite part, my least favorite part, because I get to show you how well this works, but also I have to talk about the simulations, which I normally leave to other people. So I'm going to explain them as best I can. So for this example, I'm going to make some simulations of some data at a fiducial parameter value and slightly perturbed parameter values, so I can calculate a numerical derivative. And in this case, is that blurry? That's quite blurry. Oh no, it's okay now. These are CMB polarization maps. In fact, these are the 143 gigahertz E-mode polarization maps, and they have got noise included, and they've got foreground residuals. They're not nice things to work with. So these maps, this map here is made with a fiducial optical depth of reionization of 0.055, and we've got some slightly perturbed values here. And if you see here, this is the if you take this one away from that one and divide it by the difference in the tau, delta tau, then you get your numerical derivative, and you see that this is void of your foreground. So it's void of your foregrounds and your noise and things. So this is only informative about tau. That's what I will hope anyway. Well, no, that's what it is, because they're simulations. So, just as a side thought, I would show you. I thought I'd show you. This is really blurry as well. Oh, it's okay now. I'd show you what's happening as you increase tau on the sky. So these are noiseless realizations of the CMB. And so here we have low tau, and here we have high tau. And you see that you get these large-scale sort of amplifications as tau increases. And you actually see that the amplifications get much larger as tau gets larger. So it's not linear, how this changes. It actually changes like a variance, so that's interesting. So we train the I-N. So we put our data through, we make our simulations, put our data through, calculate the covariance and the derivative of the mean, and maximize the Fisher. Here we go. You can see this is the number of epochs you've been training for, and this is how much information you are able to pull out of the network. We actually see some slight underfitting here, but it's just because this isn't the best that we ever did. We then compress the real data, so we're going to generate some real data because this is a toy example, and this is actually slightly away from the fiducial value to see how well we did at recovering the correct value. So we then draw a huge number of simulations, a huge number of parameter values, and compress those simulations, and then accepts or rejects. So here we have our points which we have drawn, and the ones in blue are the ones which we've accepted, because this dotted line here is where the summary of the real data with respect to the network. And we see we get this histogram here is a nice, fairly Gaussian curve around 0.06, which is great. The blue line is the maximum likelihood estimate. So we get the maximum likelihood estimate for free from our network. So we see how useful this is. Like, we don't have to do any extra simulations, and we get at least a first order approximation of what Gaussian approximation of what our results could be. Just interestingly, you can see that the outputs of the network are very flat across here and grow a lot here, which is very reminiscent of, if you look with your eyes, how the data changes as tau increases as well. So I think as a person, you would probably come up with the same technique of summarizing or getting confused by your data as the network does. So that's nice to know. So I'm going to go for another quick example, which will take me on to the next part and the final part of my talk. So this is some work. I'm putting my Justin hat back on for the final time. So here we've got some power spectra, some cosmic shear. So these are power spectra, and this is a very simple toy model. So we just draw a random Gaussian random field, and we put some noise in it, and we mimic some partial sky coverage. But fortunately for this problem, the analytic, the exact Fisher information is known. So makes a good comparison. So we make our architecture semi-intelligent, as in we look at the correlations using 1D convolutions in each tomographic bin, and then stack them, and then we just flatten all that and put it straight into a network. So we've done a bit of thinking. And then we train our network, and if we can see, we get another nice curve showing how much information we're able to get as the number of epochs evolves. So this is 6,000 epochs, so it's still rising a bit here, and we can get a bit more information out. But and I think the result I've quoted is on about 20,000. But just so you know, this training took about 20 seconds. So it's not a long process. It's not. If your data is small enough and it can fit in your GPU memory, then it's super quick, and you get these amazing summary statistics out. So here's our Fisher comparison. Ben will laugh because I didn't have these plots last week, but this week I do, so it's really nice. So here we have our exact inverse Fisher information, and here we have the inverse Fisher information that we calculate using our the information maximizing neural network. Across the center, this is the Fisher forecast from the information maximizing neural network, and these are actually the standard deviations of the parameters from the Markov chain, not the Fisher forecast. So we can see how close we get, and it's pretty close. I mean, I think everyone would be happy with that. Here we've got the fiducial parameter values, and we have the maximum likelihood estimator, and we can see all these. Again, these are actually extremely close, but also they're definitely within our Fisher errors. So excellent. We've managed to recover the Fisher information extremely well. The only problem is that if we now wanted to run the Markov chain, we've got to go back and do the ABC like we did for our one parameter when we're trying to infer what the value of tau was, but now in 5 dimensions, and it's just going to take a huge amount of simulations. So now my Justin hat is on. We're going to go to density estimation, likely free density. Yeah, here we go. That's it written properly at the top. Inference, Delphi, not Delphi. So we're going to use a new type of neural network, which Francois talked about the other day. So this is, in a simple way, this is a mixture density network, and it takes in some data, and you form some combination of distributions. And so here I've written a normal distribution, so this is just a mixture of Gaussians. But this distribution can be more or less anything. And you do a regression. You do a regression on your amplitudes of your different network, of your different distributions, and also predict the parameters of your distribution, so means and standard deviations if we're using a normal. And you can, this is then and then you minimize this to get, well, this is then a description of your likelihood of the of your summary statistics or of your likelihood. This is a description of likelihood. And I'm probably not going to talk too much about this, but you can just now imagine putting in your compressed summaries in here and getting out some density estimation. And really, we want to hope that by doing this, then we can reduce the number of simulations we do so to give us some example of the posterior distribution on theta. So we are able to do this using Delphi, and this is so using Delphi. We've already found that the information maximizing neural network is able to give us really good Fisher information, and so what we can do is just draw from some Gaussian where the errors come from that Fisher information, and pre-train this network on free draws from this proposal distribution. And this will get us a long way there. It won't give us the correct likelihood of the posterior at the end, but it will get us close. So then you can start drawing some. You can then start drawing some parameters, and you can do your simulations. You compress them using the IM and N, and then you put them into Delphi and retrain your network on these new simulations. And what you end up doing is just slightly squishing out or drawing in your distribution from what you learned just using the Fisher samples. And then you do that for some number of simulations, some small number, maybe like a couple of hundred simulations, and that will change the posterior distribution, the new posterior distribution, enough that you can then use that as your new proposal distribution for you to draw some more simulations and redo the same analysis where you change the shape of learn your new posterior distribution. And you can do this as many times as you need. But if we look at how many simulations we can reduce this by, if we wanted to do a full MCMC on this cosmic shear problem, then we're looking at least order of 1 million simulations. Whereas using Delphi and learning the shape of the posterior distribution, we can get there in a few thousand. So we're really reducing that number of simulations down as much as we can. So I'm going to show you just, these are some density plots. And unfortunately, I don't actually have these for using the IM and N. So this is moped compression, and we can see that we get some stretching out because it's not learned. It is slightly lossy in this case. But imagine that you had some way of compressing your data which wasn't lossy, which I've just presented. Then we can imagine that these will snug up nicely and really recreate the MCMC samples, but using a fraction of the number of simulations that you would originally need. So this just leads me on to my last point, is that I've just presented two major techniques for allowing us to do totally ignorant inference. So now we don't have to think of anything to do with the actual inference. All we need to do is to be able to model our data well. And that's it. We can model our data well. We should probably take our data well. And then we've provided that to the two networks that I've showed you today. And we can turn our brains off and get some amazing looking constraints where we've not had to work to do the compression or anything like that. So that's where I'm going to leave it. I hope if anyone's really interested, this is a summary. If anyone wants to play with this, just on my GitHub, then you should just go and play with it. It's under really, really active development at the moment as well, because we're just, me and Justin are building Delphi and the IM and N together. You should go and just try and use it. You should find bugs and tell us or fix them so I don't have to deal with it. It's a really useful tool, and everyone should go and play with it. Thanks.
So, if I understand it correctly, you're trying to feed just the maps of simulations, like CMB maps or large-scale structure maps. And then, since neural network can find any combinations, I would imagine it would find a combination which doesn't respond to the data, to the simulations, and maybe responds with some epsilon to the derivative. And how do you prevent this from happening?
So this is a problem that actually turned up quite recently. So there's a chance that what you might want to do with your data really is try and project out any tiny variance or zero variance components of your data before, as a pre-processing step, before putting this straight into the network, which actually could help. If you've got maps, then we've got very useful tools to be able to deal with, well, we've got lots of different architectures which can very easily deal with the kind of data structure we're putting in. So for example, with the HillPix maps that me and Alessandro were working on, so the CMB maps, then we've actually written a TensorFlow spherical convolution, and so we can just run that convolution and learn the weights of in this spherical space before flattening it and compressing as a fully connected app.
Well, yeah, but I mean, machine learning, I mean, it's a black box, you know, and you will always can map into null space, right? So I would imagine you would always find just your null space, right? With some, whatever, numerical noise for the derivative. So you'll have epsilon divided by 0.
Well, I mean, so one of the benefits is that if I'm going to go back I'm going to go back and it's going to go white. So we've got two parts of the network which are sensitive to the input. The first is the derivative of the means, and the second is the covariance. And these can both scale differently, which is nice because it means we can actually fix. There we go. So we can actually fix one of these if we wanted. So if we wanted to make sure that our covariance didn't go to 0, so we didn't blow up, then we can just fix this to be the identity and allow the derivative of the means to do all the scaling to still give us an informative summary. But you still have the optimal because both the covariance and the means are sensitive to the parameters. Well, but I mean, so they're both sensitive to the parameters. So if you fix this, then when you do your weight update, then you have to update your weight such that this would change, but you would backpropagate like a Lagrangian multiplier. You fix this, and then you have to update these differently so that you can keep that fixed. So because both of these are sensitive, the derivative of the mean and the covariance, we can always push all of the parameter dependence into either one of them.
Linear transformation instead of sufficient statistics is still substantial.
Yeah, exactly.
I had a question precisely related to change of variable. When you optimize your network, you want to maximize the feature information, but this is a matrix, right? So you have to make a number out of it. You can only optimize a scalar functional. So how do you turn the feature information matrix into a scalar? And can you do it reparameterization free? Or invariant under reparameterization?
So I don't know if I thought I said, but maybe I didn't. But we use the determinant of the Fisher information as our measure. So that's our scalar quantity. Whether this is invariant under change of parameters, I'm not quite sure. But we actually tried a few different scalars when we were in development, and one of them could be you could diagonalize the Fisher information and then sum up the trace. Or you could just use the trace. The trace isn't great by itself, but if you diagonalize it and then find the trace and maximize that, that's actually, that'd be a way. But
That would be the sum of the log eigenvalues, but then there are several of them before you sum. So when you optimize things, you don't know how to weight the various components if you want of the. There is some arbitrariness here in the approach.
training the network with Fisher information that's derived from assuming that the output of the network is Gaussian. So the information in a Gaussian is the result of the determinant.
Yeah.
And we're computing exactly that.
Yeah.
We're actually maximizing the information.
Right. How do you deal with the numerical derivatives there? There's numerical noise in them. For instance, you showed that the CMB maps, they were noisy. You had them at different tau values, right? So the summary statistics here are noisy too.
Yes.
Why does that not matter, or does it?
Well, I mean, it does. I mean, so when you're calculating the mean, then you just need to have several simulations to be able to calculate your mean, and you can have relatively few by suppressing your sample variance. So if you make your simulations with the same seed but at different tau values, for example, then you actually get very close. You get very noiseless derivatives already, relatively noiseless at least, if you're making it the same random initialization seed. So you can reduce it that way, and that way you get away with relatively few simulations to calculate the mean.
The consequence of having it noisy is only a slight suboptimality.
Yeah, exactly. Well, so this is one point which I didn't say really, is that I've been assuming that everything is completely optimal all the time, and and it is if your fiducial parameter is exactly in the right place, and you manage to maximize the Fisher information. But even if you don't manage to do all these things, you still end up with some amazing compression, which can still be possibly more powerful than any of your summary statistics. And so that's one of the important things. It's like, even if it's not optimal, it's still going to be really good. So you should still use it.
I used to be really interested in summary statistics and trying to learn random field models from non-Gaussian examples, non-Gaussian fields, for example. So if you ask, from an information theoretic point of view, if I give you expectation values of summary statistics, what's the functional form of the random field? It would be e to the minus some parameter times a summary statistic and a partition function, right? Mm-hmm. That depends on that. Where I'm going with this is, have you considered, it seems like you're able to almost learn the parameter that is in e to the parameter times the summary statistic. It seems like you're able to learn those parameters as a functional cosmological model. Have you considered trying to somehow turn that around and use these as in a generative sense, add a fixed cosmological model to then use to actually sample random field realizations from what you've just learned to see what they look like? And if you've really captured all the sufficient statistics, you'll see the structure that's equivalent to what you put in your examples. Oh yeah, and then have you considered automatic differentiation? There's ADOLC, automatic differentiation of code that people use. You could replace the numerical finite difference derivatives with automatic differentiation.
So on the first point,
yeah,
haven't considered that, but it's an amazing idea. So I'm gonna. So we should talk. The second point on the automatic differentiation, I think everyone should write their code in a language which is automatically differentiable, and then we always get our derivatives for free. Everyone should do that. If everyone writes their code in TensorFlow, then everyone's happy, in my opinion. Everyone else's opinion would maybe not. Yeah, exactly. So if you can do that, then that's so much better than doing the numerical ones. So. Yeah, especially because the number that you need when you suppress the sample variance is so low compared to the number you need to estimate your covariance.
Maybe one comment. If you turn it off on purpose. If you take any regular statistical model and you make a second order expansion of the log likelihood, you get the fiducial and linear terms in which you have the score function and then a quadratic term. And this is somehow like considering, if you just look at this second order expansion, it's very much like an exponential family of distribution. So in which way does what you do departs from this simple feeling about what it is to make these Taylor expansions and having the score function as the sufficient statistic?
Well, I think this is what me and Ben were kind of talking about at the beginning was maybe I don't think that was the reason why we did it, but it would definitely came to our minds that there's so many things which are related to the exponential family that it's not a surprise that we can do well with this. But we haven't really thought. Well, we talked about it quite a lot at the start, but we haven't done since. So maybe we should come back to that.
Right. Very last question.
Okay.
Okay, so just one short one. So do you have a feeling, if you, for example, train the network with a model that left, so in landed at the end, but left the mass of the neutrino vary, and then you wanted to get constrained for a conditional distribution with some fixed mass for a neutrino, would you recover the right one, or do you kind of lose information if you train the network with a model which has less constraints than the one you want to train, that you want to get inference? Okay.
I don't know.
So because the idea is that every time you want to test a new model or make inference in a new model, you have to retrain the network. So would you kind of train your network on a big supermodel with lots of free parameters and then use this to do inference in conditional models with particular values so that you can reuse what you have trained much more?
I think so. I would go both ways, mostly because you could probably do both actually, and you could compare because it's so quick to train this.
Yep. So
So that's one of the advantages. Is if you've got the simulations there at your fixed values and you have the derivatives free as well, so you can train your big multi-network. It's probably I wouldn't know exactly which one it would be because you'd have to marginalize out anything in the big model, which might then, make everything a bit more floppy. But you could always just train this. It takes virtually no time. So
maybe
I
we
would
can talk
go for
about it
both
later.
and test. Yeah.
Okay, thanks.
Okay, so let's thank the speaker and from this afternoon. Let's thank the speaker and.